entire quantity. So we'll have 1 over x squared plus 36 dx. Okay, so that's our separate step. So these just kind of stay as one entire quantity, and they move to the other side. Okay, so step 1, separate. Step 2, integrate. So we take the antiderivative of both sides. Both sides actually have the same pattern. Do we recognize this pattern? That's inverse tangent. Good. Because the numerators are just 1, that's inverse tangent. Because you wouldn't be able to sub out the x squared plus 36, for example, as a u, because there's no x in there. So part of your du, there would have to be an x, but there isn't. So we're going to have to do the inverse tangent pattern on both of them. So this one, there's a 9 here. Here there's a 36. So we're going to factor those out. We'll kind of have 2 separate u substitutions for each side. So on this one, I'm going to factor out a 1/9. So then I'm going to have 1 over 1/9 y squared plus 1 dy. And then on this side, factor out a 36 from the denominator. So I could put the, 1/36 out front. And then we'll have 1 over, this will be a 1/36 x squared plus 1 dx. Okay, so we'll sneak our u substitutions up in the margin up above because there's not a ton of room for this one. So the one on the left, this one right here, this needs to be our u squared. Like the 1/9 y squared is supposed to end up being our u squared. So if we start with u squared is supposed to be equal to 1/9 y squared. Then that means just u is equal to what?
1/3 y.
1/3 y. Good, so then du equals we got this, guys. 1/3 dy. Good. And then we want to just move that over for one last step, so we'll have 3 du equals dy. Okay, so that's our first substitution. That's going to be the substitution for the y stuff on the left. So let's swap all that stuff out. So we'll still have, we'll end up having a 1/3 out front, because this will move a 3 out front as part of the 3 du, and then that 3 will multiply by the 1/9 that's already there. So this will now be 1/3 out front. We'll have 1 over the 1/9 y squared is getting subbed out for a u squared. I still have the plus 1. And then my dy got swapped out with a 3 du. I already put the 3 out front. Okay, and then let's use maybe a v for this next one so we don't confuse ourselves. So this one, this piece right here, the 1/36 x squared, that's supposed to be our variable squared. So I don't want to use another u squared because that'll get confusing if we have the same variable on both sides. So let's say, actually, u and v look too much alike. Let's use t. So t squared is supposed to be 1/36 x squared. So that means that just t would be 1/6 x, bless you. And then dt would be 1/6 dx. And one last piece to get the dx by itself, multiply both sides by 6. So 6 dt is equal to dx. So basically the exact same thing we did on the left-hand side, just a 1/36 instead of a 1/9. Okay, so swap all that out. So we're going to have a 6 dt. The 6 is going to go out front and multiply by the 1/36 that was already there. So now I'm going to have a 1/6 out front, and then a dt at the end. And then my integrand becomes 1 over t squared plus 1. All right, so that's where we're at so far. We did double substitutions, one on the left, one on the right, and now it just is a very basic tangent inverse. So we can swap those both out. How are we doing so far? Any issues, questions? Okay, so now just take the antiderivative of both of those sides. They're both going to be tangent inverse. They're both going to have different variables, and we can swap them back in just a minute. So on the left, we'll have 1/3, and then this will be tangent inverse of u on the left-hand side. Thank you. And then equals, and then on the right, we'll have the tangent inverse of t. 1/6 times tangent inverse of t. And then remember, we always put our plus c just on the right-hand side, because it's got to go somewhere, but there's no point in putting it in both spots. Okay, so swap our variables back in. And then the last step is going to be the fun one here, is getting y by itself at the end. So this is 1/3 tangent inverse of, and then for u we have 1/3 y equals 1/6 tangent inverse of, and then t is 1/6 x, and then put our plus c on the end. All right, so we got to get to that y. So the first step is easy enough. First step is just getting rid of that 1/3. So multiply everything on both sides by 3. So we will have tangent inverse of 1/3 y. Multiply everything by 3. So on the right-hand side, we'll have 3 times 1/6. So this will be 1/2 tangent inverse of 1/6 x. And then plus c. C is an arbitrary constant. It doesn't matter if you multiply it by 3. It's still just going to be an arbitrary constant. Then do we know how to get rid of tangent inverse? Take the tangent. Good. So take the tangent of the entire side. So tangent and tangent inverse would undo each other, just like squaring and square rooting undo each other, just like e and natural log undo each other. So we take the tangent of the entire side, left and right. So when we take the tangent of the left-hand side, all we have is 1/3 y. And then on the right-hand side, take the tangent of this entire thing. Make sure that the plus c ends up in there as well. So this you actually can't simplify the same way that you simplified the left-hand side, because you have a plus c in there. In tangent inverse, you can't do, tangent of the first part plus tangent of the second part. So you actually do leave it, as gross as that looks, you leave it like that. And then the very last thing is just to get y completely by itself is multiply by 3 again. So then the 3 will just go out front of the tangent. And that is your lovely final answer. So make sure that you're not trying to take the tangent of this piece plus the tangent of this piece. There are a lot of properties that don't work quite like we wish they would, kind of like trying to distribute a power like we talked about the other day. So this actually does have to stay like that. There's no properties that we could use to simplify it any further. Okay, questions on that one? It's the algebra, really. That was the fun part there. Okay, number 5. Oh, this one's a lot better comparatively. So number 5, we are trying to just move these two terms back and forth, separate our variables. This one's a dx and a dt, so this one, x is our main variable. That's what we're trying to get by itself at the end. So get the x stuff on the left, get the t stuff on the right. So on the left with our dx, so this is kind of a transformation that we need to know trig well enough to do this. If we divide both sides by tangent, because we need to get that tangent x over to the left, if we divide both sides by tangent, what would we write on the left-hand side? What's that? I'm hearing like some mumblings of it. Cotangent. Yes, that's the reciprocal, because if I had 1 over tangent on the left, we have another trig function for that. So cotangent is what we would end up having if we move it over to the left. Tangent is sine over cosine. Cotangent is cosine over sine. So we just write it like that. So cotangent x dx is what we'll have on the left, and then 8t dt will be a nice easy one on the right. And I've mentioned to you guys before, anytime that there is a coefficient like that, leave it on the right, because you're going to have to move everything to the right side anyway, so you might as well keep the left-hand side as simple as you can and leave the bulk of everything on the right. Okay, so that's our separate step. Trig has a lot of weird things like that. So notice if you were like you know, if you're dividing by sine, you could write it as cosecant on the other side. So like knowing those reciprocals will probably be helpful when you guys are doing some of these separating. Okay, so separate, integrate both sides. Okay, so we did tangent. We did tangent in the notes either Monday, maybe even last Friday. And we don't directly have an antiderivative for tangent. Anyone remember the method that we used to get an antiderivative for tangent? Yeah. Write it as sine over cosine and then do a u substitution. So very, very similarly with this, we're going to write cotangent as cosine over sine and then do a substitution. And we might as well take the antiderivative of the right-hand side because that's going to be easy. What's the antiderivative of 8t? 4t squared, and then put your plus c on the right. Okay, so numerator's cosine, denominator's sine. Which of those pieces would you use as your u for our substitution? Has to be sine, right? Because that's sine is in the denominator. So if you used cosine, the derivative of cosine would be negative sine, but this isn't sine. It's sine in the denominator, which makes it the reciprocal of sine. So our only choice is to use this piece because it's nested in the denominator and then its derivative is in there. So we use u equals sine x, and then that means that du is equal to cosine x dx. So this just swaps out perfectly as 1 over u. Okay, so with our u substitution, our integral, so the sine gets replaced with a u. So you'd have a u in the denominator, and then this piece, the cosine x dx, is getting perfectly swapped out with a du. Just like that. And then the right-hand side is done already. Okay, left side. ln, good, so we've got natural log, and then it's absolute value. Don't forget about the absolute value part. So natural log of the absolute value of u, which should be natural log of the absolute value of sine x, equals 4t plus c. Okay, so this part was all not bad. We've got some fun algebra happening with this one too. So I purposely picked both 4 and 5 to just do 2 today because the algebra gets really intense with both of these, trying to get the variable by itself. So a couple of you guys got to a problem like this on Wednesday. Do we remember how to get rid of natural log?
Raise it to the e.
Raise it, yeah, so raise it as a power on e. So it's called exponentiating. If you remember that, great, but that's what it's called. So it's called exponentiating, where we take each of the sides and make them a power on e. So e becomes the base, and then each side becomes the power. Okay, so this part I'm gonna try my best to explain like why exactly these end up canceling out. So one thing that you can just remember is that they're inverses of each other, and inverses always cancel out, but here's kind of the real reason. So logs are exponents, and I think you guys probably remember seeing, you don't have to write this down, but something like this. You remember like log base 2 of 8, we would figure out that that was 3, and if you're trying to figure out what it is, you would say what power on 2 gives us 8. Do you remember simplifying those in pre-calc? So if you're trying to figure it out, the log means what power on this base would give me this answer, right? So if we're looking at just this is saying what power on, what's the base for this?
E.
Good, this is saying what power on E would give me sine. So this is some mystery power, right? We're saying what power on E would give me sine, and then we're taking E and we're raising it to that power. So then it'll give us sine. Right, so they essentially cancel each other out, but that's the real reason. So this part's saying what power on E gives me sine, and then we're actually raising E to that power. So it just ends up leaving us with sine. So keep the absolute value on it. And then this right-hand side, this is a part that some of you guys probably saw in the back of the book, where all of a sudden the C jumped out front, and a lot of you guys were asking me about it. So it's this weird property that comes from properties of exponents, really. And it's one that says if you have addition in the exponent like that, you can split this up as multiplication. So you can write it as e to the 4t squared and then times e to the c. So you guys will probably recognize that from like algebra. So this says if you have the same base, two different exponents, and you're multiplying in the middle, you can just add the exponents. So, I mean, a really simple example would be if you have x squared times x to the fourth. What does that give you? So x squared times x to the fourth would be x to the sixth, right? Because you add their exponents together. So if you have e to some power times e to some power, you add their exponents together. So you can also reverse that property. So this is what they're doing in the back of the book when they do this. And then they say, well, e is just a number, c is just a number. So they just write it as a c again. So if you saw this in the back of the book where all of a sudden the c just jumps out front, that's why. So they write it like that. So that's just one of those properties that once you recognize it, you can just go ahead and do that. Okay, here's more fun algebra. Do we know how to drop absolute value?
Make the other side absolute value.
Close. Do you do something to the other side? Yeah.
It's an inequality. I think sin x would be null, and then it would be greater than or equal to, like, it's something like that.
That's, I know exactly what you're thinking of, and that's if it's an absolute value inequality. So let me give you guys an example. Say we had the absolute value of x is equal to 4. What are our solutions? What could you have for x? Plus or minus 4. So the way that we technically, algebraically, drop absolute value is by making the other side plus or minus. Okay, so we can drop absolute value by making the other side plus or minus. So that's what we're going to do here. Okay, so we can drop the absolute value from the left by making the right-hand side plus or minus, but my coefficient is just an arbitrary constant c. Do we know yet if it's positive or negative? No, so does it really matter if we put a plus or minus in front of an arbitrary constant that we don't know yet? No. So technically we're dropping the absolute value by making the other side plus or minus, but it's just an arbitrary constant. We still don't know if it's positive or negative, so it doesn't really change anything if we put a plus or minus out front. Okay, how do we get x?
Take the co-function or
Not the cofunction.
Sine inverse.
Yeah, inverse function. Good. So just like with up above, we had tangent inverse, so we took just tangent of both sides. If this is sine, we're going to take sine inverse of both sides to get the x by itself. So sine inverse of both sides, then we get just the x by itself, and our right-hand side will be a lovely sine inverse of all of this. I feel like we just reviewed almost everything that you guys did in pre-calc and algebra. We covered e, natural log, trig, inverse trig, some different exponents. Got all sorts of things happening here. All right, questions on either one of these?